Thank you for the invitation to give this talk. I like to think of fusion categories, or more generally, rigid tensor categories, as analogs of groups. And the group being finite is the condition that the rigid tensor category be fusion. And of course, the underlying set of some group corresponds to the underlying linear category. Of the tensor category. And the structure maps and axioms of a group get categorified in the context of tensor categories. Two similar structure maps together with, instead of these axioms, some associator and unitor that are subject to their to their own axioms. The condition of invertibility that each element of a group G needs to satisfy gets replaced in the context of tensor categories with the condition of dualizability. And that's what is known by, that is what this adjective rigid means. It's like every object has a dual, which means the following: for every object of C, there is another object, a dual object, together with evaluation and co-evaluation maps satisfying these two conditions, known as the zigzag identities. And then that's just dualizability on one side, and then we also want dualizability on the other side, which just means you just reverse the quantifiers. You ask that for every B there's an A such that, and the very same stuff. Now, when working with rigid tensor categories, there's a very convenient graphical calculus, which tells us that the picture like this represents a morphism, in this case from A tensor B tensor C to X tensor Y tensor Z. And these are objects of C. And one important feature to note is that, to remember, is that whenever there's a horizontal line to one of these strands, it means that secretly we're using these evaluation and co-evaluation maps. So this is a co-evaluation, and this is an evaluation. And conversely, given symbols that you can use to label the strands, and a vector space for each type of box, so out of which you can select these morphisms F, G, H, and a consistent interpretation of the graphical calculus, which really what this means is a planar algebra. Then really what you have is a rigid tensor category. And now the reason why it makes sense for tensor categories to act on C-star algebras or to act on von Neumann algebras is that these, namely C-star algebras or von Neumann algebras, form the objects of a two category. The objects are C-star algebras, the morphisms are correspondences, and then you have two morphisms within correspondences. And so in this talk, I want to tell you about a couple of other possibly unrelated or possibly related situations where similarly you have mathematical objects that can be naturally acted on by tensor categories. And these are spin chains, conformal nets, and cocycles for elliptic cohomology. this being quite a conjectural statement at this point. So, spin chains. Spin chains consist, first and for all, of a choice of local Hilbert spaces and there's one for every integer, or possibly integer mod some number if you want to have only finitely many of them, if you want to put the chain on a circle, and that should be some finite dimensional Hilbert space here. And the spin chain looks as follows. And then we have local Hamiltonians, which are elements. So this is a self-adjoint operator on a tensor product of a chunk of these, where this number here is the range of the interaction. And from that data, one can form a global Hilbert space. And the global Hamiltonian, and that's the data of a spin chain. And what people often try to do with that is to try to understand the spectrum of this global Hamiltonian acting on this global Hilbert space, but that's not what we're going to be interested in right now. What we're going to be interested in is that there's a notion of, for a fusion category or for a tensor category to act on this, and it acts via defects. So let me tell you what defects are. So a defect is a rule for modifying what we have here in the neighborhood of a point. So we choose a point, and the point can be a bit thick, so we choose a thing, and then we say, okay, we don't want this here. And instead, what we're going to put is a new Hilbert space, which is here, and a new local Hamiltonian that tells you how to it interacts with the neighbors. And so the picture looks as follows. So the spin chain looks the same as before away from this point, and here we put a new Hilbert space, a different dimension, and we put some new local Hamiltonians that tells you how to interact with its neighbors, and then with that we can form the global Hilbert space with defect and global Hamiltonian with defect, which is built in the same way as here. A defect is called topological. Defect is called topological if whenever you move the location of the defect, whenever you put it at some other place with the same local data, there is a prescribed unitary intertwining the global Hilbert space here and there. And moreover, that unitary should be built only by operators involving this region between these two places. So the essentially this region here is the only. So it should be built from operators acting on these local Hilbert space, and the tensor product of these local Hilbert spaces. Being topological is extra data. It is a defect is topological if it moreover has these unitaries. And topological defects admit an operation called fusion of defects. And fusion of defects is essentially the operation of taking the two defect features and putting them next to each other. And now, very importantly, we also have the notion of homs between defects. So if I have two defects, fixed spin chain. Let's call them D1 and D2. The morphism, let's say F, from D1 to D2 is a linear map which goes from the global Hilbert space for where you put D1 to the global Hilbert space where you put D2. And let's call it again F. And moreover, we require this map here to be local. I.e., only built out of the local Hilbert spaces in a small neighborhood of the defect point. And this thing needs to satisfy a couple of conditions. First of all, it should commute to the Hamiltonian. So that's, in a sense, a way of saying that it is compatible with time translations of the system. And then it should also be compatible with space translations, i.e. compatible with these unitaries here. So let me draw the picture. And so here we have our map F. Here we have the unitary that implements the fact that D1 can be moved from one place to another. Let's call it U sub 1. And then here we have the corresponding unitary for D2, except going in the other direction. And so what do we mean when we say that this should be compatible with translation? Well, what we mean is that this whole composite here, this big thing here, should be equal to F, where F is now implemented not at this location, but at this location. Remember, a spin chain is translation invariant, and so whatever I do here, I could also do it here, and the requirement is that this composite is equal to F. And so these two operations taken together, namely the ability of fusing defects, this is all topological defect, fusing topological defects and the existence of homs between them, makes that into a tensor category. And so one can talk about a spin chain together with, well, for any fixed fusion category, a tensor functor from that fixed fusion category into this tensor category of topological defects with their fusion and their homs. And so that's an example of something on which it makes sense to act by a fusion category. Let me now tell you about something that I actually know a little bit more about, namely conformal nets. So these are, again, in some sense, one-dimensional systems where now the space is a continuum, it's R. And what the conformal net does is that for every interval, say AB, so I is an interval of the reals, the conformal net assigns to that a von Neumann algebra. So a typical letter for the conformal net is A, and this is now a von Neumann algebra. These von Neumann algebras are related in various ways and satisfy various axioms that I'm going to now list for you. So the main extra pieces of data and axioms are that, first of all, if I have a small interval inside a big interval, then the corresponding von Neumann algebras are included in each other. So I have an injective homomorphism from the one for the small interval into the one for the big interval. If I have two intervals that are disjoint, or possibly that touch at exactly one point, that's what this condition says, then when I view these both as subalgebras of some von Neumann algebras corresponding to an interval that contains both of them, then in there they should commute. And then there's a condition called diffeomorphism covariance that says that compactly supported diffeomorphisms correspond to, are implemented by inner automorphisms of the corresponding von Neumann algebras. So there exist unitaries such that these are add of these unitaries. And moreover, the various subalgebras corresponding to subintervals are transported in the expected way. So that's not the complete list of axioms, but these are the main ones, and then there's some extra technical stuff that I'm not going to bore you with. So these things, just like Spinchains, admit the notion of topological defects. And it looks very similar. So again, we have R, where now we have a defect point, where we are going to modify the data of the conformal net. So the conformal net away from the defect point remains exactly what it is, and at the defect point, we're now allowed to, we're now assigning different algebras, and that's the data of the defect, like which algebras we assign data. And all the axioms for defects are exactly the same as the one listed here, with two small modifications. So these two conditions, that one here and that one there, are now only required to hold either when J and I are both in the left half of R, so this part here, or in the right half, or if both of them contain the defect. And of course, one can also talk about the defects between distinct conformal nets, where one requires that the algebras on one side agree with what one conformal net says, and the algebras on the other side agree with what the other conformal net says, and then the algebras of intervals that go over the defect point, well, that's the new data provided by the defect. So this is the notation. D is the defect, and A and B are the two conformal nets. And I have a theorem joint with Arthur Bartels and Chris Douglas. And the theorem says that conformal nets form the object of a three category. So they are the objects, the morphisms are defects, and then there's also two morphisms between defects and three morphisms between two morphisms. And maybe this shouldn't be too surprising if you compare it to the previous situation with spin chains. In a spin chain, given an interval of this line on which the spin chain lives, we have associated to that a vector space, namely the tensor product of the local Hilbert spaces. And here, given an interval, we have a von Neumann algebra, which is one category degree higher, and so hence the 2 becomes a 3. Now, in a 3 category, we have a lot more structure. example, for every object A, let's call it A because this is the three category we care about, its endomorphisms, actually I want to take the endomorphisms of the unit defect of A. That is always a braided tensor category. And here's the proof. It's just a version of what is known as the Ekman-Hilton argument, where you take two things that live in something two-dimensional and you're able to move one across from the other. And that is the braiding in this tensor category of endomorphisms of the unit of A. This works in any three category. Here's another cool fact, that for every morphism, which I'm going to call one morphism, just to be specific, so one of these, a defect, then we can look at the tensor category of endomorphisms of the defect. That contains this thing up there, endomorphisms of 1 sub A, in its center, in its principal center. And again, this is a completely general fact about three categories, and well, I will spare you the proof of that. So let's look at some examples of defects that are going to be useful for us. So one example of a defect that always exists is the identity defect on a given conformal net. And that's just a defect that says take the real line and don't change anything to the assignment of von Neumann algebras to intervals. That's just always there. Not terribly interesting. Here's a much more interesting one, also a topological defect. It says, so remember in the axioms that one of them says that whenever I have a diffeomorphism, a compactly supported diffeomorphism, it induces inner automorphisms of the von Neumann algebras. So I have a certain number of unitaries that implement these inner automorphisms, and I can look at the sub-von Neumann algebra generated by these unitaries. That is known as the Virasoro subnet. And so my defect now is a defect between A and its Virasoro subnet, and it says if I have an interval that's entirely on the left, I evaluate A. If it contains a little bit, if it contains the defect point, I evaluate A. And if it's entirely on the right, then I only take the stuff generated by these unitaries implementing diffeomorphisms. And I think of that as being an analog of the left action of an algebra on itself, or maybe the left action of a group on itself. And so that's why I call it a left regular defect. Now let me tell you about actions of fusion categories or tensor categories on conformal nets. So because we're up by one category number, we really shouldn't be talking about actions of a fusion category on a net, but rather we should be talking about actions on defects between conformal nets. And I claim that it's particularly interesting to look at actions on this regular defect. Let me give it a name. Let me call it lambda. So now let's say C is a fusion category, and we're looking at tensor functors from C into the endomorphism category of lambda. So this depends on the conformal net A, so let's call it lambda A. Moreover, since, as I told you, this always contains a centrally embedded copy of the endomorphisms of the identity defect on A. It makes sense to require that C also contains a copy of the braided tensor category endomorphisms of the identity of A. And that the above tensor functor, namely this, is compatible with it. And so then we have a theorem which is, I mean, this is sort of well known in the field, so not due to me, saying that for every inclusion of conformal nets, let's say A sub 1 into A, we have an action as above. And now I want to conjecture, and this is very closely related to work of Marcel Bischoff, but because I'm changing the formulation from the way that he's phrasing it, I'm going to write it as a conjecture. I mean, it's not exactly the same. Says that if we further require that the action is fully faithful, and what this means is that this functor, this is a functor between tensor categories. We want this functor to be fully faithful. So an isomorphism at the level of Hom spaces. That's the analog of what it means for an action of a group on a set to be faithful. That's the analog in this setup. So if we require that, and we have this centrally embedded copy of NA, then there should be a bijective correspondence between subnets of A. So I fix a conformal net A and look at sub-conformal nets of A, and actions of fusion categories on lambda A as above. So with all this stuff, like fully faithful and with a centrally embedded copy of this braided tensor. Finally, let me tell you about elliptic cohomology, also known as topological modular forms, which is also dubbed higher real K theory because of its many analogies with real K theory. For example, both of them satisfy a version of Bott periodicity. So one of the main conjectures in the area of elliptic cohomology is by Siegel/Stolz-Teichner, which says that TMF admits a description in terms of bundles of two-dimensional quantum field theories. And if that is indeed true, then one consequence is that it makes sense to also consider these together with systems of defects, i.e. Actions of fusion categories. And this would therefore imply the existence of a version of equivariant TMF where the group of equivariants is now replaced by a fusion category. And indeed there's some evidence for that, because Jacob Lurie has indeed constructed something that he calls it 2-equivariant TMF, and that's exactly what this would be in the case when the fusion category is vec G omega. And so, yeah, so this is a very tantalizing prospect. Of course, this is completely conjectural, but here you go.